Hello everyone, welcome to the Tim Booker channel. Wishing you a pleasant listening experience. Today, I'll be interpreting a book for you. The book is titled 1, 2, 3. Infinity. This book takes mathematics as its thread and introduces significant scientific advancements since the 20th century. Starting from the basics of mathematics, it delves into the vastness of the universe. Therefore, it also carries a subtitle, Facts and Speculations of Science. Written in 1946. It has been more than 70 years since then. It's astonishing how this popular science book remains so captivating. It's almost like reading a detective novel, finishing it in just one evening. Even after all these years, this book still amazes with its charm. Considered by many as the best popular science book they've read. But what makes this book so enchanting? It sets itself apart from the usual topical science readings by using mathematics as its main thread, integrating disciplines like physics, chemistry, astronomy, and biology. The content flows effortlessly, with tight connections between ideas. Using high school-level mathematics, it can elegantly explain relativity, the dissolution of a sugar cube in coffee, or the probability theory behind it. Adding a couple of telescopes on Earth can tell us how far the sun is from us. This book provides us with a unique perspective to observe the world around us. The author of this book, George Gamow, was an eminent Russian-American scientist, a foundational figure in the famous Big Bang theory. His wide-ranging expertise spanned physics, astrophysics, cosmology, and even molecular biology, with groundbreaking contributions in each. Unlike the stereotypical serious scientist, he was known for his sense of humor, a cartoonist, and a practical joker. His colleagues described him as a big child at heart. If he were here today, he'd be considered a comedian in the scientific community. This book contains a total of 250,000 words. Now, I'll guide you through this book using 4 mathematical tools. The first tool is imaginary numbers, which take us into the realm of 4-dimensional space. The second tool is the sum of interior angles in a triangle, revealing the curvature of space. The third is probability theory, explaining the motion of the microcosmic world. The fourth is parallax, enabling us ordinary folks to take on a God's eye view, measuring the universe, from a droplet of water to the entire cosmos, from 2-dimensional paper figures to 4-dimensional space. Let's embark on a journey of mathematical marvels, a voyage through time and thought. Sure, here's the translation of the content. Good. First, let mathematics take us to 4-dimensional space. Let's start with a little preparation. Let's recall the multiplication table together. 2 times 2 equals 4, 3 times 3 equals 9. 4 times 4 equals 16. The operation of squaring numbers. Going in reverse. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. This is all easily understandable. But have you ever wondered about the square roots of -4, -9, -16? Do they even make sense? With our middle school mathematics knowledge, negative numbers don't have square roots, because they are not perfect squares to begin with. However, in practical calculations, square roots of negative numbers keep popping up. For example, consider this problem. Find 2 numbers that add up to 10 and multiply to 40. The solution initially doesn't exist. But by introducing square roots of negative numbers, surprisingly, it's resolved. Those 2 numbers are 5 plus square root dash 45 and 5 square root dash 15. Mathematicians, with their stubborn temperament, since something seemingly meaningless keeps appearing, they must find a way to give it meaning. So, they bestowed a grand name upon the square roots of negative numbers, calling them imaginary numbers. Those empty, imaginary things, represented by the letter I. The square of I is -1. So square root dash 4 is 2i. And square root dash 25 is 5i. Imaginary numbers are like the reflection of negative numbers in a mirror. Apart from being used for calculations, people couldn't really see their purpose. Until two amateur mathematicians introduced imaginary numbers on a coordinate axis. Now, imagine this. Draw a horizontal axis representing all real numbers. Where to the left of 0 are negative numbers. And to the right are positive numbers. There's no place for imaginary numbers. When we're at the 0 position, we can introduce a vertical axis to represent imaginary numbers. Points on this axis represent I, 2i, 3i, and so on. This way, both imaginary and real numbers can find their place on this coordinate system. For example, for I is on the vertical axis. If it's 3 plus 4i, then you find 3 on the horizontal axis. And 4i on the vertical axis. And they intersect. You might say this is still not very useful. But it actually has great significance. Using the I-axis, people realized that two seemingly unrelated dimensions, real and imaginary, could be combined. This ignited a revolution in physics. It helped us establish a spacetime model for four-dimensional space. The concept of the fourth dimension is often considered mysterious. And for beings like us, who only have width, height, and depth, can we imagine a four-dimensional scenario from our three-dimensional minds? It's not as complex as it sounds. There's a word we use almost every day. It's precisely the fourth independent dimension of the physical world. And that's time. Time is often used alongside space to describe events happening around us. No matter which news channel reports an event, besides saying where it happened, they also state when it happened. Therefore, all physical objects are four-dimensional. 3 dimensions for space and 1 dimension for time. Now, we want to unify these 4 dimensions into a single spatial model. Which brings up a problem. These 4 dimensions have different units of measurement. 3-dimensional space uses units of distance, like meters, centimeters, millimeters. While the time dimension uses units of time, like hours, minutes, seconds. How can we unify and compare them? We need a speed to bridge them together. In physics, there's a unique standard speed. The speed of light. With the speed of light, multiplying by time gives us distance. This allows us to view time as a kind of distance scale. For instance, astronomers say, a certain star is 5 light-years away from us. This is akin to saying it takes 5 hours to travel somewhere by train. Now, let's draw a coordinate axis, with the horizontal axis representing space, and the vertical axis representing time. This can determine the four-dimensional spacetime coordinates of an event. However, time and space have fundamentally different natures, and can't be simply unified through units. This is where the imaginary numbers mentioned earlier come into play. We match these four-dimensional spacetime coordinates with the real imaginary coordinate axis, where time is represented by imaginary numbers and space by real numbers. This way, time becomes imaginary, and space becomes real. And they're fundamentally distinct. In calculations, if we have coordinates for 2 events, we square and square root their spatial and temporal distances, which gives us the four-dimensional distance between the events. If the spatial distance between 2 events is smaller than the temporal interval, for instance, you reading a book in the living room at 8 a.m. and your mother cooking in the kitchen at 12 p.m. When calculating the four-dimensional distance between these events, what we obtain is imaginary. So we say there's an imaginary four-dimensional distance between the 2 events. Conversely, if the spatial distance is greater than the temporal interval, for example, you're reading in the living room at 8 a.m. and 10 minutes later, a meteorite strikes the surface of Mars. Then what we obtain in the calculation is real, meaning there's a real four-dimensional distance between the events. This interplay of imaginary and real coordinates has a greater significance. For objects in high-speed motion, the coordinate axis can be rotated. This rotation changes the projection of events on the 2 axes. The projection on the vertical axis lengthens, while the projection on the horizontal axis shortens. In simpler terms, for an object in high-speed motion, time slows down, and length contracts. Ah! By now, do you have a feeling of sudden realization? This is none other than the theory of relativity. Who would have thought that beneath seemingly meaningless imaginary numbers, there lies such significant physics, so profound in its implications? In relativity, we talk about the curvature of time. And in general relativity, the curvature of space also emerges. Certainly, here's the translation of the content. Good. Part 2. Let's talk about mathematics and space, where you'll witness the curvature of space. You're surely familiar with curves and surfaces. But can you imagine a curved space? Although Einstein's general theory of relativity tells us that space can also be curved, how can we, who live within space, determine if space is curved from within space? The answer is simple. Using the theorem of the sum of interior angles of a triangle. Let's imagine this. If there's a two-dimensional paper person, how could they determine if their plane is curved? The method is simple. They would draw a triangle. We know that the sum of interior angles of any plane triangle is 180 degrees. However, on a spherical surface, this theorem doesn't hold. You can imagine that. On the Earth's surface, if you draw a triangle using two meridians and a great circle, you'll have two right angles. And the sum of its interior angles will exceed 180 degrees. It's easy to see that if this paper person finds that the sum of their measured triangles' interior angles is greater than 180 degrees, then they can deduce that they are on a surface that curves up like a sphere, which is called positive curvature. If the sum of interior angles is less than 180 degrees, it's a surface curving down like a saddle shape, which is called negative curvature. Similarly, we, as three-dimensional beings, can use the same method in space. By finding 3 points in space, then stretching a string between them, we can observe if the sum of the three interior angles equals 180 degrees. According to Einstein's general theory of relativity, space curves around massive objects. And the greater the mass, the stronger the curvature. In 1915, when Einstein introduced this theory, people couldn't understand or believe it. You might think, isn't it just measuring the sum of interior angles of a triangle? Isn't it simple? Just prove it. Find a massive object, like a mountain. Place 3 pegs around it. Stretch a string. Measure the string and angles. But even if you choose the biggest mountain, like the Himalayas, the conclusion will remain the same. The sum of the 3 angles' interior angles is exactly 180 degrees. This is because even a massive object like the Himalayas isn't enough to curve space to a measurable extent. To prove his theory, Einstein looked for a more massive object. The sun. He proposed an experiment. Find a point on Earth. Attach a rope, extend it to a star. Then pull the rope to another star, finally returning to the original Earth point. Crucially, the sun should lie within the triangle formed by the rope. According to the general theory of relativity, since the sun curves spacetime around it, the sum of these angles shouldn't equal 180 degrees. If we don't have a long enough rope, we use light instead, since light always travels the shortest path. In practice, we don't need to measure all 3 angles. We only need to measure the apparent angle formed by the light from 2 stars, as it passes near the sun. This apparent angle should differ when the sun is inside the triangle formed by these 2 stars, compared to when it's outside. This experiment has a necessary condition. It can only be done during a total solar eclipse, because the sun's glare makes it hard to see other stars. Thus, it wasn't until 1919, during a total solar eclipse in West Africa, that the British astronomical expedition successfully conducted this experiment. They observed light from stars passing near the sun, indeed bending, proving that the sun's mass indeed curves the surrounding space. Einstein went further and formulated an even more crucial theory. Gravity is the effect of spacetime curvature. This reframed gravity not as a force but as a result of space's geometry. When the sun's mass curves the surrounding space, planets move within the curved space, rather than the sun pulling them with a force. It's akin to saying that on a curving highway, you can only travel along the curved path. From the above two parts, it's evident that Einstein's achievements in physics are closely tied to mathematics. It can be said that both the special theory of relativity and the general theory of relativity analyze motion phenomena using mathematics. Let's take a look at the third point. How does probability theory explain the movement of the microworld? Let's examine the motion rules of molecules. If you observe a glass of water with the naked eye, you can't detect any signs of movement. However, if you magnify the water by millions of times, you'll see its distinct particle structure, composed of numerous tightly packed individual molecules. Now, you can clearly observe that water is not in a state of rest. Its molecules are in a state of intense agitation. Imagine shutting a highly excited crowd into a room. In fact, molecules of all matter constantly undergo irregular motion, known as thermal motion. Thermal motion of molecules doesn't require heating. In fact, only at temperatures below -273 degrees Celsius, absolute zero, do molecules come to a halt. For example, the salt in the pickled vegetables and salted duck eggs we eat utilizes the continuous motion of sodium chloride molecules to infiltrate eggs or vegetables, making them salty. This is a classic application of molecular thermal motion. Given that thermal motion is random, can we calculate the trajectories of molecules? Indeed, there's a way. Mathematics is that magical. While it may not give the exact trajectory of each molecule, it can provide the most probable trajectory. Interestingly, the trajectory of molecular motion is similar to the path a drunk person takes while walking. A drunkard's walk is a famous mathematical problem. Imagine a drunkard leaning against a lamppost in a square. Suddenly, it decides to take a random walk. It takes a few steps in one direction, then changes direction and takes a few more steps, repeating this process and turning randomly. After many turns, the drunkard ends up walking a curved path. For example, after turning 100 times. How far is it from the lamppost? At each turn, the situation is unpredictable, seemingly unsolvable. Now, let's solve this problem using rigorous mathematical methods. Simply draw two coordinate axes with the lamppost as the origin, and apply the simple Beta's theorem. We can establish an infinite equation. If the drunkard turns n times, the equation spans from 1 to n. Now, this problem can be approached using statistics. Since a drunkard's walk is random, the likelihood of walking in both directions is equal. Thus, the more steps taken, the more erratic the trajectory. This lengthy equation, after some simplification, yields a straightforward result. For a drunkard who has turned n times, the most probable distance from the lamppost is the average length of each segment, multiplied by the total number of turns n. For instance, if a drunkard takes just one step before turning, then after 100 turns, the distance from the lamppost is 1 times 100, which is 100 meters. As the number of turns increases, and more steps are taken, the calculation becomes more accurate. Now, let's replace the drunkard with molecules. Imagine injecting a purple solution of potassium permanganate into a glass of water. Observe how it diffuses through the water. Each molecule of potassium permanganate behaves like a little drunkard, colliding and changing direction due to the impact of surrounding water molecules. These molecules experience tens of thousands of collisions and turns per second, while only traveling a fraction of an inch per turn. Based on our earlier derived formula, it would take approximately 10,000 seconds, or almost 3 hours, for the purple potassium permanganate molecules to diffuse 100 times farther. Approximately an inch. Perhaps you don't need to calculate. Common sense tells us that diffusion is a slow process. Otherwise, when adding sugar to coffee, why do we keep stirring it? To help dissolve the sugar faster. However, I'll tell you. Molecules move at speeds of up to 576 km per hour at room temperature. To put it in perspective, The latest high-speed trains can reach a top speed of 350 km per hour. Despite this rapid thermal motion, molecular motion seems serene and calm. With this probability formula, we can explain this phenomenon effectively. Let's consider another example for clarity. It takes 8 minutes for light to travel from the sun's surface to Earth. However, a photon takes a staggering 50 centuries to travel from the sun's core to its surface. This illustrates how slow diffusion is. We realize that when the number of objects is small, we can only perform vague probability calculations. As the number of objects increases, considering billions of molecules' motion, we adhere to the strict laws of diffusion. From an uncertain state to the most probable, most certain state. Or from a low probability event to a high probability event. We have the famous second law of thermodynamics, also known as the law of entropy. Entropy represents disorder and chaos. Any spontaneous change in an isolated system increases the system's entropy. When entropy reaches its maximum, the system reaches equilibrium. For instance, on a mahjong table, when tiles are stacked up, entropy is low. When shuffling the tiles, entropy is high. When milk is added to coffee, initially, they remain separate. With time, they mix, and entropy increases. Not only does entropy increase, but in the absence of external forces, the process is irreversible. When you build a sandcastle in the desert, the wind quickly scatters the sandcastle, returning it to a state of disorder. However strong the wind, it can't restore the sandcastle to its original state. Just like a broken glass, it can't spontaneously reform. This law also explains why the arrow of time is unidirectional. Alright. Finally, we transition from the micro to the macro world. Let's delve into the fourth question. How is parallax displacement used to measure the universe? When discussing the application of mathematics in the macrocosmic universe, there's a multitude of examples to explore. Today, we'll focus on a fundamental question. Measuring sizes. Let's see how mathematics assists us in understanding the size of Earth, the size of the solar system, and even the size of the Milky Way galaxy. After humanity realized the Earth was a sphere, naturally, a question arose. How large is this sphere? In the 3rd century BC, the renowned Greek scientist Eratosthenes devised a method. He heard that in the city of Syene, upstream of the Nile, at noon on the day of the solstice, the sun cast no shadows, as vertical objects had no shadows. However, in Alexandria, where he lived, at noon on the solstice, the sun formed an angle of 7 degrees with the vertical. This observation inspired Eratosthenes. He hypothesized that if a straight line was drawn, starting from the sun at Syene and extending to the center of the Earth, then drawing another line from the center to Alexandria, the angle between these two lines would equal the angle at which the sun illuminated Alexandria, 7 degrees. 7 degrees represents nearly 1/50th of the full circle's 360 degrees. Hence, the entire circumference should be 50 times the distance between the two cities. Ultimately, Eratosthenes calculated that the Earth's circumference was 40,000 kilometers. Close to today's precise value of 40,076 kilometers. This calculation, more than 2 millennia ago, was remarkably accurate. However, the significance of the Earth's first measurement is not solely in its precision, but in the realization that it was exceedingly large. If Earth was this vast, how enormous was the world beyond our planet? Thus, the first question of astronomy arose. The distance between Earth and the Sun. This is the key to humanity's understanding of the universe's size. To measure this distance, scientists invented a method called parallax displacement. The principle is quite simple, and you can experience it by using your fingers. If you close one eye and hold out a finger, you'll notice that your finger's position seems uncertain with only one eye. Distance cannot be accurately judged with a single eye. However, when observing an object with two eyes, they form a false angle with the object. And our muscles sense this angle's magnitude, allowing us to reliably determine the distance. This effect is called parallax displacement. Now, equipped with astronomical telescopes at two different Earth locations, we can observe the Sun like using two eyes, measuring the angle between them. However, the Sun is still incredibly distant. Scientists need the rare astronomical event of a solar eclipse to calculate solar parallax, which, through geometric methods, enables the determination of the Earth-Sun distance. In 1761, an international scientific competition emerged, similar to an Olympic event, where the best scientists from around the world scattered to over 100 locations on Earth, all to solve astronomy's first problem: the Earth-Sun distance. The result was a distance of 133 million kilometers. This preliminary measurement revealed the scale of the solar system. Yet, humanity continued to venture into space, towards the stellar realm. This required transitioning to the world of stars, and the parallax method was still applicable. However, even Earth's farthest points couldn't provide distinct parallax against the vast backdrop of interstellar space. Nonetheless, a solution was found. Given that we knew the Earth-Sun distance, why not use Earth's orbit to measure star distances? In other words, we could measure the parallax of stars from Earth's position at its closest and farthest points from the Sun, which correspond to January's perihelion and July's aphelion. Scientists could step beyond the confines of the solar system, just as if using a ruler, to measure the universe's scale. This led to the successful measurement of the star 61 Cygni in the constellation Cygnus, which was found to be 69,000 times farther from Earth than the Sun. Yet, a challenge arose. The limitations of parallax prevented measurements beyond 400 light-years. Due to the smallness of the parallax angle, scientists discovered a new method: the Cepheid variable stars. In the 18th century, a British teenager, with extraordinary eyesight, identified certain stars with regular fluctuations in brightness, akin to a heartbeat, pulsating rhythmically. These stars were Cepheid variables. Though he died young, this resilient youth pioneered new astronomical measurement methods. Scientists found a mathematical relationship between a Cepheid star's brightness and its period of variability. In other words, by determining a Cepheid star's period, its absolute brightness could be calculated. Subsequently, based on the inverse square law of brightness and distance, the distance to the star could be deduced. Astoundingly, Cepheid variables were discovered in various star clusters. Thus, scientists measured the distant reaches of the Milky Way. Furthermore, if a Cepheid variable star is found in an extragalactic system, its distance indicates the distance to the entire galaxy. Consequently, we measured the Milky Way's diameter at 160,000 light-years. And the nearest galaxy, Andromeda, is 2.54 million light-years away. The dimensions of the cosmos truly boggle the mind. Today, we know the universe has a definite size, with a diameter of at least 921 light-years. This doesn't imply that a barrier exists at that distance, declaring no entry. Rather, it means the universe is a finite, boundaryless, self-contained expanse. Remember the cosmic analog of the Bay Area we discussed in Part 2? The universe possesses a definite, expanding volume. Imagine a cosmic explorer in a spaceship. Despite traversing vast cosmic distances, they will eventually return to their starting point. Sure, let's summarize one last time. In this book, we've introduced 4 mathematical tools to you: complex numbers, interior angles of triangles, probability theory, and parallax displacement. They've propelled or shaped concepts such as special relativity, general relativity, the second law of thermodynamics, and cosmic measurement. It can be said that a significant cornerstone of scientific advancement is mathematics. It bestows us with deeper and higher realms of thought, enriching our sensory experiences, and aiding us in expanding the frontiers of the unknown. From unity to infinity. It embodies both the progression from the simple to the complex in mathematics, and the advancement from the shallow to the profound in science. The uncharted territories within the universe remain vast, boundless even. But how does that matter? Each inch of progress brings its own joy. And what if the truth is infinite? Now, from unity to infinity, this book concludes here. Congratulations on completing yet another book. We express gratitude for your support and attention. Please subscribe to the Tim Booker channel. Give it a thumbs up, and share this valuable knowledge with friends and peers around you. Together, let's combine wisdom with action. Achieve our financial goals. And create a brighter future. Thank you all, and farewell.